Deep in the silent expanse of space, an explosion of unimaginable power rips through the darkness. It's an event so catastrophic, so energetic, that it makes even the brightest supernova look like a gentle flicker. This is a hypernova, the most powerful cosmic detonation known to science. And it releases more energy in mere seconds than our sun will generate over its entire 10 billion-year lifespan. Imagine a star, not just big, but a true celestial titan, a giant among giants. When these massive stars reach the end of their lives, they don't just quietly fade away. They go out in a blaze of glory that tears apart the very fabric of space-time with a force that defies comprehension. A standard supernova is already mind-bogglingly powerful, but a hypernova is something else entirely. It releases over 10 to the power of 45 joules of energy. That's at least 10 times more powerful than a regular supernova. It's so intense that it launches twin jets of superheated matter, plasma, and radiation at nearly the speed of light, creating a scale of destruction that stretches our understanding of physics to its absolute limits. But what pushes a star over the edge to become a hypernova? What are the specific conditions that trigger this ultimate cosmic fireworks show? The answer, scientists believe, lies in something called the Collapsar Model. It all starts with the star itself. We're not talking about your average star. We're talking about true cosmic behemoths. At least 30 times more massive than our sun. These stars live fast and die young, burning through their fuel at an astonishing rate. As they age, they forge heavier and heavier elements in their cores through nuclear fusion. The process continues until they create iron, and iron is where the trouble begins. Unlike lighter elements, fusing iron doesn't release energy, it consumes it. Suddenly, the outward pressure from fusion that has supported the star against its own immense gravity for millions of years just stops. The core, now made of dense iron, can no longer resist the crushing weight of the star's outer layers. Gravity wins. If the star is massive enough and, crucially, if its core is spinning incredibly fast, something extraordinary happens. The core doesn't just collapse into a neutron star, as it would in a regular supernova. Instead, it collapses all the way down into a rapidly rotating black hole. This newborn black hole is the engine of the hypernova. As the surrounding stellar material spirals into its gravitational abyss, it forms a swirling, superheated accretion disk, like water circling a drain, but on a cosmic scale and at unimaginable temperatures and speeds. The intense magnetic fields and extreme conditions within this disk launch two powerful focused jets of matter and energy. These are relativistic jets, meaning they travel at a significant fraction of the speed of light. They act like colossal drills, punching their way out from the core through the collapsing star's outer layers. These jets are the source of another incredible phenomenon, long-duration gamma-ray bursts, or GRBs. These are the brightest and most energetic electromagnetic events ever observed in the universe. For a few brief brilliant seconds, a GRB can outshine every other star in the observable universe combined. It's a beacon of cosmic violence, visible across billions of light years. The hypernova itself, the visible explosion we see, is powered by a different mechanism. The incredible heat and pressure within the jets and the surrounding material forge vast quantities of radioactive elements. For a long time, the connection between these two extreme events, hypernovae and gamma-ray bursts, was just a theory. But that all changed in 1998. Astronomers at the European Southern Observatory were observing a supernova designated SN 1998BW. It was unusually bright, far brighter than a typical supernova should be. At the same time, a gamma-ray burst, GRB 980,425, was detected coming from the exact same region of the sky. It was the smoking gun. For the first time, scientists had direct observational evidence confirming the link between a hypernova and a long-duration gamma-ray burst. The Collapsar model wasn't just a clever idea anymore, it was a reality. Fast forward to 2023, and our understanding took another giant leap forward. The Zwicky Transient Facility, an automated survey telescope, detected an event so bright and long-lasting it shattered all previous records. Officially named at 2021 LWX, it quickly earned the nickname Scary Barbie. This cataclysm was located 8 billion light-years away and was 10 times brighter than any supernova ever recorded. It wasn't a short-lived burst either. It shone with incredible intensity for over 3 years. Scary Barbie released a staggering 1.5 times 10 to the power of 46 joules of energy, setting a new record for both cosmic brightness and duration. While its exact cause is still debated, some theories suggest it was a supermassive black hole tearing a star. A part it highlights just how extreme the universe can be and how much we still have to learn about these cosmic titans. But hypernovae are not just agents of destruction, they are also profound creators. They are the ultimate cosmic forges. Inside the fiery heart of these explosions, the extreme conditions create heavy elements far beyond iron, in the periodic table elements like gold, platinum, and uranium. When the hypernova erupts, it blasts these newly forged elements across interstellar space. This enriched material seeds the surrounding gas clouds, providing the raw ingredients for the next generation of stars and, crucially, for planets. Every atom of gold in a piece of jewelry, every bit of platinum in our electronics, was likely born in the heart of an ancient, violent, stellar explosion, like a hyper. In a very real sense, they are the reason we exist. Life as we know it depends on a diverse mix of chemical elements, and hypernovae are one of the primary mechanisms for distributing them across the galaxy. However, this creative power comes with a dark side. A nearby hypernova would be absolutely lethal. The intense radiation, particularly the gamma rays and cosmic rays, would be devastating to any life in its path. Scientists theorize that a hypernova may have been responsible for one of Earth's major mass extinctions. The Ordovician-Silurian extinction event, which occurred about 445 million years ago, saw the demise of around 85% of marine species. One leading hypothesis suggests that a hypernova occurred within a few thousand light-years of Earth. The resulting gamma-ray burst would have stripped away a significant portion of our planet's ozone layer, leaving the surface exposed to deadly levels of solar radiation. This would have caused widespread damage to the ecosystems that dominated the planet at the time, triggering a global catastrophe. This raises a natural, and slightly worrying, question. Could it happen again? Are there any stars nearby that could go hypernova today? Astronomers keep a very close watch on massive stars in our galactic neighborhood, particularly red supergiants like Betelgeuse in the constellation of Orion and Antares in Scorpius. Both are massive stars, nearing the end of their lives, and they are prime candidates for future supernova explosions. However, we can all breathe a sigh of relief. Both Betelgeuse and Antares are over 500 light-years away. That's far enough that even if one of them were to go hypernova, which is considered unlikely, as they may not be massive or fast-spinning, enough the effects on Earth would be minimal. The gamma-ray burst would be aimed in a random direction, and the chances of it pointing directly at us are infinitesimally small. Instead of a threat, their eventual explosions will provide humanity with the most spectacular celestial light show in recorded history, a new star in the night sky visible even during the day. Hypernovae are a haunting and beautiful reminder of the dual nature of the cosmos, a place of both creation and destruction on an epic scale. They represent the most extreme endpoints of stellar evolution, shaping the structure of galaxies, forging the elements that build new worlds, and dispersing the very seeds of life across the cosmos. They show us that from the most violent and destructive events imaginable, the universe finds a way to build anew. They are a testament to the powerful, relentless cycles of death and rebirth that govern everything, from the smallest atoms to the largest stars. Thanks so much for watching. If you're fascinated by the raw power of the universe, make sure to hit that subscribe button and ring the bell so you don't miss our next journey into the cosmos. See you next time.